All right, we're going to move a little bit back into some theory here and talking about kind of the n space and how we use vectors to talk about things in that space. So the definition of a vector space is if you have a set of vectors that actually exist, they're not empty. We define two operations, addition and multiplication. So those have to be defined. Most of the time we're going to define it just with normal addition and multiplication, like what we know to be true, but it is possible that like we define addition as subtraction or something. I don't know, like there's different things that might be defined there. So that will be given to you in the problem, as well as like what multiplication means in that space. So again, we'll look at some examples. For the most part, they'll be defined as normal, but you will always have them defined. So these are going to be true. We're going to say that the sum is u plus v. It's true that you can reverse u and v in the addition, like that's fine. It's okay to not have to add things in the same order because it's just addition. There's a zero vector, such if you add zero, then you get the original vector. There is a negative vector that gets you to the zero vector. There's a scalar multiple, okay, that is also in the vector space. And these things about that scalar multiple are all true as well. So this example and solution is from our textbook. It says, let V be the set of all arrows, directed line segments, in three-dimensional space, and two arrows are equal if they have the same length and point in the same direction. So essentially we're talking about vectors here in this vector space. We're going to define addition to be the parallelogram rule, so how we defined addition back in chapter 1. And we're going to define multiplication to be the absolute value of c times the length of that vector, still pointing in the same direction. So if you have v, okay, then 3v points in the same direction and it's 3 times as long. Now, if we have a negative, okay, it says here pointing in the same direction if c is positive and pointing the opposite direction if it's negative. So pointing this way, but still that multiplier is the length. So if it's negative 3v, then you would have a vector that looks like that for negative 3v. The definition of v is geometric. We know what length and direction look like in a plane, okay? An arrow of zero length is just a single point. It's the zero vector. It is true that if you have a v, then negative 1 times v is just the negative. Okay, so let's look at some of these axioms and talk about what would be true. So it says 1, 4, 5, 6, and 10 are evident. Addition is normal. The zero vector exists. We've talked about the negative vector. Multiplying is just normal. And then 1 times the vector, that works as well. The thing that we need to kind of look at graphically is 2, 3, and then 7, 8, and 9. So here we have the parallelogram identity because that's how it is defined. So you would be able to add u plus v and get that vector. You could also add v plus u, and I know they don't end in the same spot, but you just need their length and direction to be the same. Those are the same, okay? Now here, if you add u plus v and then add w, so u plus v is here, and then add w to it, you get that, okay? But if you take u and you add v plus w to it, then you actually get the exact same vector and it's equal to whatever it is without parentheses. So we can see that here. Now, if you add, subtract any multipliers here, you're going to be able to show that these things are all true as well. So again, if you had like 2u plus 2v, you would be able to graphically show the same way that 2v plus 2u gets you the same vector, maybe in different spots, but the same vector, same direction, same length. Okay, and then very similarly with the 3 as well. This also expands to polynomials. You've been doing this in your algebra and your pre-cal and all your classes beforehand. We just didn't call it that. So polynomials are a vector space. They have addition. So if like here's your f and here's your g, then f plus g, you can add polynomials, okay, just like you would anything else. You can also have scalar multiplication. So if you have a number times f, you take that number and you multiply it by, or fc, here, this one's 2g. So if you have 2 times g in this example, then you take 2 and, oops, I have the answer there. Multiply it by 2 plus 0.5t, and that gets us 4 plus t, which is this here. So polynomials fall into the definition of vector space under their normal definitions as we know them.